So we've already talked about torque. We've already talked about torque a little bit, and this concept has to do with rotations also. So when we think about torque, you recognize the section number in the textbook, right? Torque was sections 8.3 and 8.4. This comes before torque, but it's not needed to learn about torque at all. So what we're going to do today is talk about a new unit of rotation. What do you measure rotation in? What units do we use? Give me some units. Sorry. Clockwise or counterclockwise is our direction. Very good. What else? Degrees. Good. What else? If you go several of these, what do you call them? Rotations or revolution. Either one is kind of interchangeable. You're good. Now, we're going to talk about a unit today called radians. And in your math course, you're going to learn about this in the fourth quarter this year. So another nice tidbit you're going to get in physics before that. And I'm going to go through what you need to know for physics about radians, whereas in math, you might go into a little more depth about radians. Then we're going to talk about things like angular position. As an object rotates, the angle that it passes through. So this is going to be a great preview for your fourth quarter trig section when you get to next quarter. Then we're going to talk about acceleration and speed, specifically with angles. And then later, at the end of this, we're going to talk about the equations of motion. Remember the big three? X equals VIT plus 1 half AT squared, or VF equals VI plus AT. We're going to do all three of those and show how they're analogous with rotations. So it's not like new three formulas that you have to memorize at all, actually, which is nice. They're the exact same thing, but for angles instead of linear displacement. We're going to talk about angular displacement. So let's do that to start. First, let's talk about this first phrase, angular position. So the angle an object makes with respect to some reference line. And traditionally in math courses, you'll see that reference line written as like the x-axis. So let's say this is the angle right here. This angle may be 60 degrees. So this is like the initial side in math. You're going to hear about this. And this is the terminal side, it's called. And the idea here is really that just, you know what? You're going to change from one location to another by doing what? By rotating. Okay, this is a rotation. This is a rotation. It's not in this case a distance that we're traveling. Now, we'll talk about how those are related. If you ever think about, what if you walk around a circle? What's the distance you travel? Well, it's a fraction of a circumference. And you've known that from geometry. Right? If you walk 180 degrees of the circular path, that's just half of a circumference. Because we should know by now that 360 degrees is one rotation. So this is the concept we're going to look at for angular position, how it changes. Now, to do this, we're going to have to make sure that we understand that we have directions, and we've already mentioned these, so we don't have to go over them again. We did this with torque, okay, but I'm going to emphasize it just by circling them. But it's the same concept there, the same adaptation of how we're going to think about our directionals for vectors here. Now, for radians specifically, this is going to be our new unit. This is what's interesting. Now, radians I'm going to talk to you about as a conversion factor to degrees in a minute, like centimeters to inches, there'll be a conversion. But what's interesting about radians is actually a radian, by definition, is the angle, and I'm going to show you in the diagram, the angle for which the length of the arc is equal to the radius of the circle. So in this diagram, the length of the arc itself, I'm going to highlight in red, is right there. And it actually happens to be the same length as a radius for this swept out area. So the blue radii that are shown there are some length that R, or 2, or 5, or whatever you want to call it. Well, what's in red is the exact same length. That's what the definition of I never knew this in high school, by the way. I only knew how to convert radians to degrees, and that was fine, because I learned how to do it. But I never actually knew what the background behind a radian was. And it's the angle for which, again, the arc length of a circle will equal the radius. And this happens to be an approximation we can use too. So that's what the definition of a radian is, but a radian is around 57.3 degrees. Now, and look at the angle on the diagram. That's reasonable, right? It's definitely less than 90. We could all see that. This would be 90. Okay, so it's more than 45, you can tell, but it's not obvious that it's 57.3. Well, 57.3 sounds arbitrary, and it kind of is right now. But what we do want to know is this, and this is what's really interesting. And some of you may know this from if you're studying for the SAT in math right now. How do you convert radians to degrees? What's the conversion factor?
Pi over 180. I mean,
Yep.
they know the 180 equals pi over 180.
It's pi 180, yeah. Pi 180. Good morning. He is not. I think we put him on the attendance. Yeah, sorry about that. No, okay, bye. All right. Yes, a pi radian, the word, or the value of pi radians, like 2 radians, 7 radians, like this is 1 radian right here. 1 radian is about 57.3 degrees. Well, it turns out that, and this is nice, it's not convenient, or it's not like, it's not coincidental. It has to do with the geometry of the circle, and this is what you're going to learn more about in math. Pi radians is 180 degrees, because 2 pi radians is defined as 1 rotation. Again, think about that for a second. 2 pi radians is 1 rotation. The whole concept behind that is going to come from what's called the unit circle in your math class. And the unit circle is a circle where the radius is 1. What would the circumference of a circle be if the radius were 1? What would the circumference of a circle be if the radius equals 1? 2 pi, 6.28. I missed the pi, I got the pi here. So it's not just 2, it's 2 pi. Because remember, the formula for the circumference of a circle is 2 pi r. And I'm saying if r is 1, it just becomes 2 pi. 2 pi is the distance around what we call the unit circle in math. And 2 pi radians is where we get the concept that it's 360 degrees. Now, what you need to know for physics, this is a little detail, and I'm trying not to go too much theory. What you need to know for physics is this. Radians are a new unit of angle displacement. Just like we had centimeters this year, and meters, those are new to you, aren't they, for the most part? Those that were, raised in the US. You use feet and miles and that stuff. Well, you learn and recognize meters is something new. Radian is the new unit for degrees that we're going to see. And you're going to use this a lot in physics and in math going forward. It's a little more complicated in a sense, but it's not anything new, is what I'm trying to get at. Okay? It's nothing new than what you've seen with degrees before. And this is your conversion factor. Just like we know a conversion like 2.54 centimeters, you might not know this one, but 2.54 centimeters is 1 inch. Or 5,280 feet is a mile. Conversion factor is all we're looking at. Now, which conversion factor are you going to use? You could use either of them. I happen to use this one all the time. And I think most math teachers instruct you to just convert by multiplying by pi over 180 or 180 over pi. And that's really the one that's most useful. But it is good to know this right here, and we'll see that a little bit later on. So the unit of radian is very important. Let's go on to the next thing. This is called arc length. Arc length. And this is also something you're going to learn in math in the 4th quarter. So you're really getting a nice preview. So something that you guys should ace this when you get to it in the 4th quarter, because you're going to see a lot of it in this section. And this is a good benefit to you. S is the length around a circle, and it's only a sector of that circle. So let's start with a circle. And let's go ahead and draw an angle from the center, like a slice of pizza. The red is S. Blue is R. And theta is the angle intercepted by that arc. And you may have seen this already in geometry last year. You may have done S equals theta R, but because it's in radians, I don't think you did it in geometry. In geometry, I think you guys said, how would you find the arc length if the angle is 20 degrees? Would you do 20 out of 360? Because the whole circle is 360, right? Everybody with me in this? The whole circle is 360? So if your angle were 20 degrees, it'd be 20 out of 360. So you could take the circumference and multiply by the fraction 20 out of 360. Or if it's 180 degrees, 180 degrees is how much of a circle? Half a circle. So if you wanted the arc length for half a circle, you could do the whole circumference and then divide by 2. So there were ways to determine arc length when you were in geometry. This is just a new way to do it. But the key is this, and circle it. Oh, the value of theta has to be given in radians for this formula to hold true. That's the key. Theta cannot be in degrees for this formula. The other way to do it with using a fraction out of 360 makes sense to use degrees, because degrees for 360 makes sense. But for this formula, you're going to use radians for your angle theta. That'll be the unit. Let's look at an example of this. Let's look at an example. So determine the arc intercepted by a central angle of pi over 4 radians for a circle with a radius of 0.5 meters. So let's start by listing our givens. Central angle, what variable is the central angle going to go down as? What is it? Good. So don't let the word central confuse you. Just know when you hear central angle, it's the angle of rotation. Okay, if something's rotating in a circle, it's the angle of rotation when you hear central angle. So that's pi over 4 radians. And the radius is given as 0.5 meters. And our goal is simply to find the arc. Determine the arc, I should say length of the arc. I just wrote these notes last night. If you want to add that up here. Okay, determine the length of the arc there. So go ahead and use the formula and plug in. All you're literally doing is multiplying those two values. Multiplying those two values. Now here's the thing, and this is where it gets a little bit funky. That's why I said radians can be confusing. And I'm going to quickly talk about this, and then I'm just going to let it go. And I'm going to say, you know what, just we'll assume that it's understood. And I know it's not something that's going to be like very obvious and clear. The answer will have what kind of units? What am I looking for here, guys? What am I actually looking for? What is the word? Length. Length. So what are the units? Meters. Now, that's where it gets weird, and I understand it. If you look at your units, it doesn't make sense. These units are radians. These units are meters. How is the answer only a unit of meters? Where do the radians go, right? And I'm doing this as pi over 8, because what's 0.5 really? 1/2. So 1/2 times pi over 4 is pi over 8. You see where this number came from? We can put a length. Let's put an approximate length so I'm not confusing anyone. The approximate length is around 0.39 meters. Now, but I want to point out the fact that, again, where did the radians go? Where did the units go, right? So radians and degrees, units of rotation, are not actually, okay, they're actually units that are unitless. I know, exactly. They're units that are unitless. And this makes no sense, and I've read about this for a long time, and I get it because the math makes sense, but like the idea behind it doesn't. But they are units that are unitless. And here's the concept. If I were to multiply something by radians here, it doesn't act as a unit multiplying the other value. Just like if I had degrees, it wouldn't act like that. Now, if I multiply something though with kinematics later, like radians per second, times the number of seconds, my answer will be in radians. So all I want you to recognize is this. Sometimes in certain equations, maybe put a little asterisk, when you multiply something with radians, that radian doesn't take effect at all. The actual unit is carried down from here. So just write yourself a note that radians aren't used in the unit of the answer for this formula. Maybe Mr. Hall will do a better job at explaining that, but I don't think he's going to go into units because in physics is where we really look at units. So he's not going to be going into units with meters and radians and stuff. But radians, believe it or not, is actually not a value that has units. It's technically considered unitless. If I can come up with a better way to explain that, I will, and I'll get back to you. But it's not something that you really need to worry about right now, is what I'm saying. So the next thing we're going to look at is angular velocity. What was velocity? Literally, what was velocity back from the beginning, chapter 1? What was it? I heard d over t, I heard change in distance. D over t. Now that was speed. What was actually velocity? Not d over t. What is it?
If you mean displacement.
Yeah, displacement or x over t, or y over t for displacement over time. That's what we were looking at. Now, in this case, we're not looking at velocity that's linear. We're not looking at a length, right? This is my velocity that's linear. It's a length that's changing over time. What's changing now over time is not a length, but an angle. This is like when you think about motors and cars and RPMs, revolutions per minute. That's how fast something is spinning. Angular velocity. how quickly an object rotates or swings. I use the word rotate if it's making a full circle and it's continuing like a motor, or I can use the word swing if it's just like an arm that swings open or closed. Nick?
Isn't that W just equal to torque or something? I remember seeing that on the, 1 over torque, right?
So that, on the formula sheet,
Yeah,
right?
'cause I saw that yesterday.
That W stands for frequency a little bit later on. So we're going to use that W as a different variable. And I might change that to F now. I used to use W on, it's omega by the way. This is called omega.
Okay.
O-M-E-G-A, it's the lowercase symbol. It's one of the Greek letters. But Nick, later on we're going to change, I think, that omega to F on the formula sheet.
Okay.
I'm going to reprint the annotated tau.
So you saw it yesterday.
Yeah, I get it. And that tau is not torque in that application, that's time period.
Oh, okay.
Time period. Now, back to the idea here is that it's how much an angle changes, how quickly an angle rotates. So if I do this, right, 45 degrees versus this, and the second one was clearly faster, right? Everybody sees that? Because what did I do? I covered the same delta theta, 45 degrees, but I did that the second time much faster. So I had a smaller time period. Smaller denominator means if this goes down, this must go up. They are indirectly related to each other. Inversely or indirectly related. Now my units for theta in this application are in radians, and my units for time are in seconds. Not degrees per second, not rotations per minute. If we get something that's in rotations per minute, we'll convert it to radians per second. All right, I mean, you can see the analogous nature. I don't really have to write it because we already said it, but look, there's the analogous nature right there. These are both speeds or velocities, right, in a sense? These are both like displacements. One's an angular displacement, one's a linear displacement. And then these are both time. So what I want you to recognize here is this. You're not learning a new formula. You're learning new variables, really. The formula, the setup of it, is identical, and it's going to be to all of our kinematic formulas that we've learned already. Except where you have velocity, now we have angular velocity. Where we have displacement, now we have angular displacement. The change in position, how much the angle changes. And time is still, fortunately, time. Okay, time is still, fortunately, time. It's going to happen a couple other times. Let's look at the second and third examples. So this is actually right out of something I found in my grandma's house. I moved into Brooklyn years back, and I used to live there. And my grandma has like an old school Italian house with all this like old artifacts and stuff, and a nice little music box. And it rotated, and I was trying to estimate the rotational speed. It was about 1.5 rotations or revolutions per minute. And we want to determine this angular speed in radians per second. So this is just asking you to do a conversion, this problem. So 1.5 revolutions per 1 minute. And I want to convert that into radians every second. So this is simply dimensional analysis from chapters 1 and 2 of the year at the very beginning, but now using rotational units. So first I can get rid of minutes. Minutes are in the bottom. Let me put minutes up top. And I want to get seconds in the answer, so I'll put that in the bottom. Again, I see, right? So I see that this is revolutions per minute. That's revolutions per 1 minute. Minute is in the bottom. I put it up top. These will cancel each other out. Radians per second. I'm going to try to get to there eventually. So right now I can tell myself, well, there's 60 seconds, so let's fill that in 1 minute. So remember how I told you guys how to do this? Always fill in the units first, then put the numbers. It just makes sense. It's logical. So I got rid of minutes, and now I'm in, ready? Look what I'm in. I'm in revolutions per second. But what do I want to be in?
3 degrees per second.
But what's one revolution
3
in terms of degrees or...
Yeah.
Half of
It's 540 degrees to be 1
Okay.
radian.
Right? How we should go back in our notes and look at it, because we wrote it down. What is it? One revolution is 360 degrees, which is how many radians? 2. Look back. Scroll up. Come on. It's not 2. 2. What is it? 2 pi radians. It's 2 pi. No, okay. No. Go back and look. Guys, we did. I'm going to pause so you can value. So I'm going to take, in this case, multiply by. I want to get rid of revolution. Let's put that in the bottom. Well, how many radians in a revolution? Let me make that in yellow so it's a little more obvious. How many radians in a revolution is our 2 pi radians for every 1 revolution. Revolution cancels in 2 spots. And look at my units now. I've got radians here. I've got seconds here. So I take the 1.5 by the 2 pi, divided by 60, and I'll have my answer in radians per second. I'm trying to erase it, it's not working. What do we get in radians per second? This will be a relatively low value of radians per second.
0.157.
Yeah, around 0.16 radians per second. I can't erase that circle. I do not know why. This program sometimes doesn't like to erase all stuff. Yeah.
If it's 1.5 revolutions, would it be 3 pi?
If it was 1.5?
Yes.
Yeah, it would be 3 pi. Absolutely. Good point.
So why is it 2 pi radians?
I got.
Because remember, I have the 1.5 here already, right?
Yeah.
So 1.5 times 2 pi is how many? Right?
Okay,
That's the 3 pi. So Nick, you think of it that way also. Okay?
Yeah, that's
Right? So you're just replacing 1 minute with 60 seconds, and then, so 1.5 would be divided by 60, but then you have to make 2 pi, and then just.
Why 2 pi?
Because remember how many radians, what was our conversion? What are the radians? It was 2 pi radians was 1 full cycle, 1 revolution.
How would you know to put 1 revolution there?
Because remember, see it up here? I want to get rid of revolution, and I want to get into what? What does it tell me? So I put this unit here in the beginning to remind myself I need radians in the top. So to get radians in the top and get rid of revolution, we put revolution in the bottom so that these units cancel. And the conversion between radians and revolution is seen right here. There are 2 pi radians in every 1 revolution. So this conversion factor is like saying 3 feet in 1 yard. Right? You know there's 3 feet in a yard, most people, or 4 quarts in a gallon. You know that from when you're a kid? Or 2 half gallons in a gallon, right? That idea? That's a conversion factor. So this is a new one. That's why it looks unfamiliar. But this is something that you'll get to know. That 2 pi radians is going to be 1 full revolution. So if I ever want to get rid of revolution as a unit, I put it in the bottom there because it was starting up top, and then I have my radians at the end. Conversions are going to be important here because we're going to have a lot of problems that are starting revolutions per minute. So you have a physical idea, an understanding of it, and then we'll convert that to radians per second. Radians are not as clear because it doesn't logically make sense because it's a new unit to you. Right? If you hear radians per second, it means, well, that's 0.16, and radians is 57 degrees, so like, what does that really mean? But if you hear something in revolutions per minute, that's actually pretty reasonable. You can get an idea of what's happening. This little music box is making 1.5 revolutions in a minute, which means it must be going slow. Have you ever looked at the inner workings of a music box? It's incredible, actually. The way it works, the soldering pieces that are there that cause the keys to deflect, it's unbelievable the way it works. And the timeliness of it, and that's why it's cyclical. Because once it makes 1 rotation, what does it do? The song starts back over. So that's the cyclical nature behind the music box. Yeah. Anyhow, that's the point here. Let's do a second example of this so we get an idea a little bit better. So, and I'm giving you the value in this case, but I have RPMs in parentheses. So this is an actual value. Helicopter blades swing with angular speeds of around 450 RPMs, which I'm showing you here is 47 radians per second. So I'm not having you convert here. But if you want to, I would recommend practice converting from 450 RPMs, revolutions per minute, like we just did, to radians per second. Maybe when you're home practicing with the homework, also convert this. But for now, just accept it. Through what angle in degrees will the blade rotate in 8 seconds? Now, I want you to think logically, people. A helicopter blade. Visualize it. How fast is that thing spinning?
very fast.
Right? I mean, 450 revolutions every minute. So in 8 seconds, I want to know how many degrees it takes. So I could say 8 seconds out of 60 seconds and find the fraction and say, oh, it revolves 20 times. And then 360 degrees for every revolution, I can figure out like that. I can do that, old school math ways. But I could also look at this problem and think, well, we've got one formula so far. That one formula says omega equals the change in the angle over the time period. That's the formula that we're given. And this makes sense to use this formula because what are we given in the problem? Let's see. We're given omega equals 47 We're given the time period equals 8 seconds, and we're trying to find through what angle does it rotate. We're trying to find theta. Soon I'm going to drop delta, by the way. I would usually use it, but your book did, so I kept the delta there. Delta just means the change in the angle. But if we're talking about angular velocity, the angle must be changing. Okay, you're going to hear about that. Like, think about it logically. If something is spinning with angular velocity, the angle that it covers must be changing.
If you have, okay, so what do you mean, if it says, does RPM stand for radians per minute?
RPM stands for revolutions, write this down, revolutions per minute, or rotations per minute. You can think of it either way. When you hear about a motor, you'll hear the word rotations per minute.
I thought it stood for radians per minute, so then I divided.
Converted that to radians per second, yeah. No, if it's radians, it'll be RAD always. It'll always say rad. RAD for radians always. In all books, it will say that. So now our goal is to find delta theta. How do I get delta theta by itself? How do I get rid of that time?
Multiply 8 by 47.
Yeah, let's multiply. Very good. So let's bring the time up with multiplication here. Time cancels on the right side. And we get 8 seconds times 47 radians per second. Now here's where you're going to get really annoyed with me. Because a minute ago I said, ignore the unit radian. Remember it didn't matter? Where S equals theta R, radian we kind of ignored. Here we're not going to ignore it. Because look, what cancels? Seconds cancels with seconds, doesn't it? 8 seconds is the time times 47 radians per second. What unit will my answers have then?
Radians.
It'll have radians. This is not like a trick question. Yet earlier I was telling you that radians were unitless, right? They don't actually matter in the problem. In these problems with angular velocity and rotations happening, radian is your unit of rotation. What does this number turn out to be?
376.
And that's great. But what did the problem ask us for? What angle in degrees? In degrees. I just underlined it in the problem. In degrees. Well, we got to go ahead and convert. Careful for that division. I'm in radians. What do I want to get to? I want to get to degrees. What's my conversion factor? I want to get rid of radians, and it's currently in the top. So where do I have to put it to get rid of it? In the bottom. What do I want to get to? What do I want to get to? Good? I want to get to degrees. That's what the problem is asking. How many degrees are there for how many radians? What's our conversion factor? That works, but that's an estimate. Give me the one with pi. Pi is the one we're always going to use. And how many degrees? Pi radians for how many degrees? 180. Just look, you can look, it's fine. You don't have to memorize it yet. So it's pi radians for every 180 degrees. Again, this is simply a conversion factor. We wrote it down earlier. It's one of the few conversion factors you will ever really have to memorize. Only because, honestly, you're going to use it in math so much this year, you will benefit from memorizing it in physics. Trust me on this one. Right? I mean, for those, I know you said you study for the SAT subject test right now, right? So you've seen this before? Because it's on there. So you have it memorized. You pretty much have to have this concept memorized that pi radians is 180 degrees. Or 2 pi, if you double this, this becomes double. 360.
So you can do that.
Yeah. Or I could say a half a pi and make that 90.
Okay.
Right? I could just change the both by whatever. But this is the base conversion that we're always going to use. Julia, 57 is right, but that's an approximation. It's 57.3 because pi is irrational. That approximation is not as useful. We use pi instead. So when we get an answer here, 376 times 180, radians cancels in both spots. Cross them off. What do I get in degrees? It's a huge number, right? And think about why it's a huge number. It's a helicopter spinning. It's going to make a lot of revolutions. So how many degrees are swept out? You forgot to divide by pi.
57.
Oh, it's right.
So you take 376 times 180, do that first,
Yeah, 21,000.
and then divide that answer by pi. And this answer is reasonable, again, because of the nature of the problem. Think about a helicopter blade rotating. In 8 seconds, it's going to rotate a lot of revolutions. And we could have figured it out. Take your calculator out. Let me show you this. You can do, now I want you to use the math we're doing, but I want to show you how you could have done this last year. Take your calculator out. Ready? Here's what you do. I'm going to wait till you have it out so you don't do it at the same time. It's actually really like, so this is like, if you ever did like math competitions, or if you're into like riddles and stuff like that, you can solve this without these formulas. Just use proportions. He's already doing it here. I'm watching. So it's 8 seconds, right? And we know that it's going to rotate 450 revolutions in 1 minute. 8 seconds is how many minutes? It's 8 out of 60, right? That's how much of a minute it is. 60 seconds is a minute. So do parentheses on your calculator. 8 divided by 60. And that's the fraction of a minute that's occurring. Hit enter. Take that and multiply it by 450 revolutions, because there's that many revolutions every minute.
60.
So again, you're going to take 8 over 60, that fraction, 8 over 60, and then multiply that by 450. That'll give you the amount of revolutions. But because there's 360 degrees in every revolution, multiply that answer by 360. And you should get, you probably get 21,544 or something. I think it's rounded.
600.
Is it rounded? Is that why?
No.
It must be. We must have been rounding something here. You're not getting this exact same
I
number?
think you rounded 377.
Oh, here's why. Here's why. When you did 8 out of 60, did you use the exact answer?
Yes.
47 times 8, 376, times 180, over pi. 21,543, okay. And you're telling me when you do 8 out of 60?
Yeah,
Oh, you know why? 47 is rounded from 450. 450 revolutions per minute is actually 47.3 or something radians, and that's why I said around 47. You see that? That's why. I apologize. It's not. There's no real discrepancy. This, you got 21,600, is that what you got? Yeah, because this should really be around 47.3, I think. 47.3 times 8 is a little bigger, which makes this answer a little bigger, 21.6. Around. I realized because I was estimating, so it was an integer last night. But I want to give you the idea that you can do it as a fraction of a minute and then RPMs. But again, in physics, I want you to do it this way because you have formulas that allow you to solve for the angle theta that we're looking for, and then just convert that answer. All right, let's finish with one more thing I think we're going to talk about. Yeah, we'll do one more thing and maybe go into a quick example of it. I find this example to be exciting. So we're going to relate angular speed to tangential speed. First of all, what was tangential speed from chapter 9? It was section 9.1 and 9.3. What was tangential velocity or tangential speed? What was the idea behind it?
2 pi over r.
That's how we calculated it. Good. 2 pi r over time. That's how we calculated it. In the lab, we did that. But what was tangential speed? Tell me about it. What was it? When an object did what? What was the object traveling? What do we call that? Circular motion. When an object traveled in circular motion, it had a velocity when it traveled along that path. We call that the tangential velocity or tangential speed. So we are physically talking about in this problem an object that's rotating. Let's say the center is here. Let's say it's the rubber stopper. And the rubber stopper is rotating like this. You're swinging it over your head, and there's a rope connected to it. Okay? So it's the rubber stopper lab. Imagine a bird's eye view of it. So as you spin this rubber stopper, we said in the lab that it has some velocity tangent to the circle. And we drew that velocity vector literally like this always, right? We drew a velocity vector like that. Or when it got to the next position, the velocity vector looked like that. And the velocity vector was always tangent to the circle, meaning that it had some velocity keeping it in motion. Well, we can relate that to its angular velocity. And remember, the angular velocity is how quickly the angle is changing. The angular velocity is how quickly the angle is changing. And this is our relationship in that. The velocity that's tangent to the circle will equal the radius times the angular velocity. Again, provided that the angular velocity is in radians per second. That's the key here. It's got to be given in radians per second. Every time it's in radians per second. So what we're going to do is this. If I tell you that something is rotating at a certain angular speed, say 3 RPMs, we can convert that to radians per second, and then if we know the length of the radius here, we can find the velocity of the object that's spinning. So the rubber stopper, we could have found its velocity if we knew the angular velocity itself. Well, let's look at an example where this can come into play. So determine the tangential speed of a person on the surface of the Earth located at the equator. And then I follow up with, what about a person at the North Pole? So I'm going to see if Mr. Don checks our apparatus, just because it'll be worthwhile for this. He just took a couple of straws, like this, and made like a North and South Pole. So the Earth, remember I was talking about how it's tilted, right? So the Earth is tilted like this, and when it's tilted, it spins like this. The straws are the axis of rotation. Everybody with me? North Pole here, South Pole here, equator here. Now, in one rotation, logically think about this. A person on the equator must travel a longer arc length around than a person up here. Think about it. Follow my finger as it rotates. And my body as this rotates, my finger would outline this arc length right here. But when the person's on the equator, they would traverse this arc length right here. So what about the North Pole? A person smack on the North Pole as it rotates. What are they doing? They're really not moving. They're rotating, but they're not covering any arc length. Is that clear? So their tangential speed, remember, tangential speed is the distance covered, the arc length over time. This person, though, is going to have 0 tangential speed at the North Pole. But at the equator, what distance from the center is a person? What do we call that? The blank of the Earth. What's the word for it? Okay, from the center of the Earth to a person on the outer part of the Earth, you would call that the Earth's radius. One radius length. Think about it, right? One radius length. Only people on the equator. And let me explain and give a quick spherical diagram. All right. So a person on the equator takes the blue path right here. A person in New York takes the red path right here. Takes the red path right here. A person at the North Pole, as we said, literally just sits there. They rotate, but they don't cover any distance. So as we get closer to the equator, the amount of distance covered is greater. So people on the equator are the ones that are spinning with the fastest tangential speed. In New York, we're spinning slower, and at the North Pole, they're not spinning at all. Or they're not moving in linear distance at all. Yeah?
Isn't it after you hit 360 it'll go back down again?
After you hit the equator, you mean?
Yeah.
Yes, it goes. It's the same concept in the South Pole. Yep, absolutely.
So it's like a swirl. It's tiny at the North Pole, and then it gets bigger.
Exact. And then when you get to the South Pole, it gets back to being smaller again. So if we're going a smaller distance, we must be going slower. So let's calculate this. So our formula that we just wrote down a minute ago is this. Vt equals R times omega. Now, we're trying to find Vt. R is really the radius of the Earth. All right, that's this length right here. Take a look. In the diagram, I'm going to put it. Whereas if I'm in the red circle, if I'm in New York, can I use RE as the distance? No, because this is the RE. This is not RE. This is shorter for sure. So we're only going to focus on the equator for this one. So the distance we're going to use in this problem is actually the radius of the Earth. And omega is going to be the angular speed of the Earth. Well, how fast do we rotate? Give me units. How fast do we rotate? Angular. We make one revolution every. That's okay. That's the around the sun. One rotation every 24 hours every day. Sorry, I should say rotation, not revolution. I use the word revolutionary. The Earth revolves around the sun, but the Earth rotates about its own axis. So omega is going to be the value of 1 revolution per day. That's really what we're looking at. And the radius of the Earth I can look up is 6.378 times 10 to the 6th meters. Can I do this? Can I multiply these? What do I need my units to be? What did we just say? Go to the previous slide. What should the units of omega be? Omega should be in radians per. And right now it's in 1 revolution per day. Here's my conversion. Let's quickly do it together. Omega, 1 revolution per 1 day. I want to get rid of revolutions and put radians. So put revolutions in the bottom, put radians in the top. Revolution in the bottom, radian in the top. How many radians are there in how many revolutions? What is my conversion factor between radians to revolutions? Good, 2 pi radians, I like it. Is how many revolutions, Kim? 1 revolution. I would agree with that. So far we have canceled revolutions. We're in radians per day, but we want to be in radians per second. Let's cancel revolution so we see it happen. Next, reduction of units. Next. I then want to multiply to get rid of days. Days are in the bottom. So I put days up top. There are 24, give me a second, 24 hours in 1 day. 1 hour is 60 minutes. And last but not least, 1 minute contains 60 seconds. So look at this conversion here. Watch, just everybody watch, look up. Day cancels with day. Hour cancels with hour. Minute cancels with minute. I'm left with radians per second. So what is my number? Well, this is 1 times 2 pi times 1 times 1 times 1. So 2 pi. 1 times 24 times 60 times 60. So my value is going to be quite small in radians per second. It will turn out to be 7.3 times 10 to the negative 5. That's the value that we're going to use to calculate this. Okay, so please finish this up tonight right here. Finish up your velocity. Use the radius of the Earth and use this number, 7.3 times 10 to the negative 5 for omega E. There's homework at the end of this. It is not due tomorrow. I haven't put a due date yet, but you absolutely can start it. I would highly recommend it because we only have we're through half the notes. We're 2 pages through the notes at this point. Okay, we're about 2 pages through. Yeah? All right, have a good day, guys. By the way, this answer comes out to be in miles per hour, around 1,000 miles per hour. 1,000, yeah. 1,000 miles per hour. Which is kind of crazy to think about it. If you're on the equator, you're traveling at 1,000 miles an hour and you don't even know it. You don't even feel it. Again, I'll take labs. Back row, forget labs.
I misnamed my problem set. I said it's problem set 6. I'm sorry. What?
Problem set 6 was the second one.
Oh, sorry. Yeah, so it is 7. Wait.
It is 7.
Oh, yeah. Okay, I'm sorry. Yeah.
You did not submit problem set 6 at the end of the second quarter.
Okay, no. It's possible.
And that problem set 6
Yeah.
and lab 8 were the last 2 grades. Oh, you're doing
Jack, did you manage to get to the tone homework? Is it in? Put it in now. Show me. I want to.
All right, let us go on. And let's talk about this next topic called angular acceleration. So we already spoke about how fast something spins. And the rate at which something spins we called angular velocity. But what if the thing that's spinning starts spinning faster? How many people have their acceleration? Very good. How many people have their permit or their driver's license at this point? Or have driven at least in a car? Legally. More hand goes down. What you'll notice is when you press the gas or if you change gears, you can physically hear the motor changing. And this is mainly for like someone who uses a manual, but even in automatic, you hear the car go like that, literally. You hear the vibration changing. The motor speed in RPMs, rotations per minute, is physically changing. So there's some sort of acceleration happening angularly. So that's what acceleration that's angular is. It's the rate at which your angular velocity changes. If the angular velocity gets faster, that means the acceleration angularly is positive. If the angular velocity slows down, or speed slows down, it means the angular acceleration is impeding its motion, or negative. So let's take a look at 4 examples of this. With a diagram here. So here's our 4 examples, and these are very similar to what we did earlier this year. So let me give you an example of this. So earlier in the year, I posed the question the following. If we're walking with positive velocity and we have negative acceleration, what's happening to us? If we're walking with positive velocity but we feel negative acceleration, what must be happening? We're slowing down. And that whole idea was, oh, well, if your velocity is positive, but acceleration is negative, those are opposites, so you're slowing down. Okay, second scenario. If I'm walking with negative velocity, and yet the acceleration is positive acting on me, what am I doing? I'm walking with negative velocity, but acceleration is positive. What's physically happening? You're still slowing down. Good, when you fall into the track. You're still slowing down. When are we speeding up?
When they're both in the same direction.
Very good. Whenever the sign of velocity and acceleration are the same. So if I'm walking this way, and then my acceleration pushes me this way, I'm getting faster. Literally. That's what this diagram is showing. The first 2 scenarios are if we have rotation, and it's rotating angularly with acceleration in the same direction. So in this first scenario, the object is moving counterclockwise. That's the direction of motion because the angular velocity tells me that. But it's also accelerating counterclockwise. So it must be speeding up. Again, it's rotating this way, but its acceleration is also this way, so it's going to get faster, 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 faster in the same counterclockwise direction. So the speed is increasing, is what we could say. And we could say the same thing for the second scenario here, except that it is rotating clockwise. The angular velocity is positive. The angular acceleration, is negative because it's clockwise. The angular acceleration is also negative, but if they're both negative, it was like the example where if I walk across the room this way with negative velocity, and there's negative acceleration pushing me faster this way, I'm going to speed up, but in the negative direction. So this angular speed increases. Okay, but the difference is this is in the counterclockwise direction. This is in the clockwise direction. But in both cases, this, what do I want to call this thing? I would say gear, but it's not a gear. What is it called on a boat? Well, I guess it's a steering wheel or something, right? We call it that.
What's a valve?
No, it's the thing that sticks out of the back. What's it called?
Oh, not that. I meant the thing that the main guy, the main captain
Yeah, the
uses. Helm?
Yeah.
So as he or she rotates the helm, you'll notice with boats sometimes if you don't hold it, it'll spin on its own because the water is causing you to change or wind is coming in. So this is like a pulley system or a helm or a gear rotating. But in general, I want you to recognize that speed is increasing in both these scenarios because the angular velocity and the angular acceleration are in the same direction. Okay? They're in the same direction. That's why it's happening. Now, because you guys are smart and can use logic, if we have 2 things acting in the same direction in both cases and it's both speeding up, what can we conclude about the other side of this scenario, Helen? They're going to be slowing down. Speed decreases. And why is that, Helen?
Because they're going in opposite directions.
Good. It's rotating, in this case, it's rotating clockwise, but the acceleration is counterclockwise. So it's like this, ready? It's rotating like this, rotating like this, rotating like this, and then something says, I want to slow you down the other direction, or I want to give you some acceleration in the other direction, so the speed will naturally decrease. So what we notice here is that omega and alpha are in opposing directions. Okay, that's why I circled those and labeled them up there. Again, the concept is that these are in opposing directions. These are in opposing directions. But if they're both in the same direction, when they're both in the same direction, we speed up. But when they're in opposing directions, we would slow down. Or the rotating object would slow down. Okay, so the same exact assumption we made with linear velocity. It is analogous, right? We talk in physics about how you need to model things. So if it's a projectile like a rocket, we might model it as a point in space. If it's a full-size car, we might just model the center of mass of the car. Here, we're taking the same concept and we're using the model from linear velocity and extending it to angular velocity. All right, let's get into an example using angular acceleration now. God bless you. I'll start with the formula at the top right so we remind ourselves what it is. Okay, there's our actual formula for this. God bless you. So we are looking at example 5. And example 5 says you step on a stationary skateboard. So the skateboard is stationary. And you kick off to begin to ride it. If the angular acceleration of each wheel is 1.8 radians per second squared, how long will it take before they are rotating at 12 radians per second? So the problem with this problem, the issue with this problem, I noticed right away, is that everything's in radians and radians per second, which is what we need, but we don't have any physical understanding of what that means. So don't let that confuse you. If it's given in RPMs, we've been converting to radians per second. So we have an idea of what it physically means because it started as an RPM. But for these problems, they're going to be starting in radians per second. So you might have any physical understanding of the problem itself. So maybe toward the end of the problem, you want to convert things to radians per second or rotations per minute so you have an idea of what you're actually doing. So let's start by listing what we know. The angular acceleration of each wheel, that's alpha, is 1.8 radians per second squared. 1.8 radians per second squared. How long will it take? That means time. So we're looking for time. It started as a stationary skateboard. Stationary means not moving. And then finally, how long will it take before they're rotating at 12 radians per second? That's going to be the final rotational velocity, or angular velocity. So I tried to use a little color coding here so you could see where things came from. By the way, I always forget whether I say things or not in each class. I didn't mention this yet, but I said alpha a minute ago. This symbol is called alpha, just so you know. Angular acceleration. That symbol looks like a little fish. It's called alpha. Just like the one that looked like a W was called omega. Again, Greek symbols, right? Greek symbols we're going to notice here. All right, so what's our goal here? Our goal is to find time. So we have the formula, alpha equals the change in angular velocity over time. And please, 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 I can't say this enough, make sure you use final minus initial. Final minus initial, final minus initial. A lot of people have been forgetting that on tests, on labs. Remind me, I'm going to give you a lab back next period, actually. I have to turn back. And you'll see that some people keep mixing up initial and final. It's got to be final minus initial when you're looking at change. So let's see, what are we looking for? We're looking for time. So let's solve for time. So to solve for time, we'll just switch. All right, remember that? What we've done a couple times already this year? Rotate or switch diagonally. So to get time by itself, we switch these two parameters. Omega I was 0 because it had no angular velocity to start, so that's going to definitely be 0. So let's take that value of 12, right? 12 will go in right here. 12 minus 0 all over 1.8. And feel free to call this fish instead of alpha if you want. It doesn't matter. Yeah, when I was in high school, we called it fish. I don't know why. But call it alpha if you like. It doesn't matter either one. Is that what it is?
Yeah.
It's like the Jesus fish?
Yeah.
I think I've seen that somewhere here. All right, so what do we get?
6.67.
All right, nice. Around 6.67. And my units are going to be what?
Seconds.
Nice, Nick. Because it's a measurement of time. It's a measurement of time. So again, let me just reiterate what we did here. We recognized that the problem involved an object that was getting faster and faster and faster, skateboard wheels, as the person pushes on the skateboard. Okay, as the person pushes on the skateboard. So this person would have to push on the skateboard for about 6 or 7 seconds. So it's a little while to get up to speed, and then maybe he or she, instead of pushing anymore, just stands on the skateboard and coasts at a constant velocity. And once he or she coasts at a constant velocity, that would mean that omega would stop changing. Think about that logically. If you're on a skateboard or a bicycle, and the bicycle or skateboard is just coasting at a constant velocity, the speed at which the wheels are rotating is also constant. It's got to be. If that speed is faster and faster and faster, the bike would also get faster and faster. Okay? So this is called angular acceleration. Just like we had acceleration earlier in the year. And can we focus on physics, please, and stop swiping up and down and typing and other things? And people, there's 8 people in the room right now. You don't think I'm like noticing stuff? Come on. So let's relate angular acceleration to tangential acceleration. So again, as an object spins faster and faster and faster, we could say it has angular acceleration. But if we were to physically put a point on the circle right here and recognize that it's got a certain velocity, but let's say that that velocity suddenly gets bigger, right? Look at the vector length. It goes from a relatively slower velocity in red to a faster tangential velocity in blue. The only way that the tangential velocity would get faster, and think about the lab, is if you spin it faster, faster, faster yourself. So for that to happen, for this tangential velocity to become greater, there must be some tangential acceleration. And this is analogous to the other formula we used earlier, where we wrote, I'll put it in the top right, we wrote this formula earlier. It's the same formula really, except instead of velocity, now we're looking at acceleration. Think about the one on the top right, Vt equals r omega. Instead of Vt, it's At. Instead of omega, it's alpha. So that whole equation in red is about velocity being angular or tangential. But the whole equation here is about acceleration. But they're really very similar to one another. So what are we asking about here? We're trying to say, if this thing spins faster, how much faster is V getting? That's what we're doing in this problem, okay? If it spins faster, if there is some alpha present, some angular acceleration, how much faster is Vt getting? That's what we're physically doing here. Now, with that said, let's look at an example of this in this problem. 6. An airplane propeller, this is actual fact, or actual values are correct. An airplane propeller takes around 3 seconds to get up to a rotational speed of 1,900 rotations per minute. Determine the magnitude of the tangential acceleration at the tip of the 2-meter radius blade. Now, for things that are rotating, even if you don't know how to draw it, just draw a radius. Here's the center, right? Draw the radius of 2. And recognize that we are looking at the point on the tip of the radius right there. But if you know how to draw an actual propeller, a propeller would look like this. And this would be the radius of 2. And it would be rotating about the center of the propeller. And our point of interest is still that x. So whether you actually draw a propeller, you don't know what a propeller were, it doesn't matter. Don't let it confuse you. If it's rotating and you're told it's got a certain length, a radius given, just draw a vector from the rotating point to the point on the outside. It's 2 meters in length, 2 meters. Now, let's see what's going on here. We're told that the airplane propeller takes 3 seconds, so that's our time, to get up to a rotational speed of 1900 RPMs. What is that then? Not R, why are you saying R? That would be radius, right? What's the variable we're going to use? You're on the right track. It is F, but what is it? What is it? Omega F, yeah. Omega F, right? Remember, Brandon? Angular velocity. Well, we're going to use that new formula in a minute, but we just have to list what we have given first. And how do I know that this is omega? Because it's radians per second, or rotations per minute, or rotations per hour, or rotations per second. It has to do with how much it spins in a given time period. That must be angular velocity. Now, that's angular velocity. What did it start at? What kind of an angular velocity? Why 0? Yeah, it says to get it to move up to that speed. So we have to make the assumption that it's 0 to start. It's got to be assumed really here. We finally also know that the length of the rotor is 2 meters. Or propeller, not rotor, propeller. It's 2 meters. So our goal is to figure out the tangential acceleration. That's what it says here. So we're trying to find out what AT is. And as we know, the formula for AT is the following. AT equals R times alpha. I've got R, so I've got half the problem, but I don't have alpha. How can I find alpha? Huh?
Alpha equals changing W over T, changing omega.
Alpha, the angular acceleration, is how much your angular velocity changes over the time period. So, really, we could figure out the change and go ahead and find alpha to use in this equation. What's the one problem that we might run into right now? Units. Good. Units are not in seconds. So this is rotations per minute, and we need to change it. So let's multiply by a conversion factor or 2 here. Take a look at where I'm putting my conversion factors. This is 1900 rotations per 1 minute, but I want it always in radians per second. So I want to get rid of minutes, which are in the bottom. So I'm going to put minutes up top. I'll put seconds in the bottom. There are 60 seconds for every 1 minute. Then, I don't want this to be in rotations anymore. I want it to be in radians, the other unit we've talked about. So I want to get rid of rotations, which is currently up top. So let's put rotations on the bottom. How many radians are there per rotation? 2 pi. Let me cancel my units accordingly. Minute, minute. Rotation, rotation. And I'm left with radians per second. I'm left with radians per second. How do I get the number for this? Well, yeah, good.
Multiply 1900 by 2 pi and then divide by 60.
Exactly. 1900 times 2 pi, all divided by 60. Remember, numerator, 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 multiply those 3. Divide it by whatever the denominator is here. So 1900 times 2 pi over 60 yields around 199? Around 199 radians per second. So that's the omega F that we're going to use. That's the angular velocity. That's the angular velocity of the propeller once it's up to the running speed. That's how fast it's going to be rotating. We know it started from rest. It's going to be rotating this fast. It took 3 seconds to happen. So I can go ahead and find alpha. I can go ahead and find alpha over here because alpha is the change in my angular velocity over time. My angular acceleration is final minus initial all over time. 60 what? 66?
Well, yeah.
Is it 0.3 or what is it point?
0.3. Well, depending if you don't round it, it'll 66.32, but if you round it, 66.33.
199 over 3 should be repeating.
Yeah.
66.3 repeating? Got it.
Why are we talking about like WI and WF? I thought we were talking about the formula AT equals RF.
We were, yep, and it's right here. You see it? But what's the problem? We have R. Do we have alpha? Look at the formula. Look at the givens we have. We were given rotations. We were not given alpha. But alpha has a definition from yesterday that we finished with. This was alpha that we looked at earlier. Alpha is the angular acceleration, how much it's getting faster and faster and faster and faster, because omega is how fast it's going, is changing. It starts from rest and it starts to speed up to this fast in that much time.
So how are you supposed to know that that's what you're supposed to...
Look at your units. Remember I always talk about units? What are my units given as? 1900, see RPM? Remember yesterday I told you guys to write down what RPM means? RPM means rotations per minute.
Okay.
If anything is given like rotations per minute or radians per second, that's always going to be alpha when it's like this. But when the denominator is squared like that, radians per second squared, that's what alpha is. So if in a problem you're given units that either say RPM or radians per second, that's got to be alpha. Jot that down. Write a note for yourself. It's the units that tell you. RPM or radians per second imply alpha. Imply omega, your angular velocity. This value gets plugged in here. This value gets plugged in here. We get a tangential acceleration of 132.7 meters per second squared. And why is it meters per second squared? Because remember, this is, imagine a point on the surface that's rotating. This point is rotating faster and faster and faster and faster and faster. So it's moving in meters per second, but since it's getting faster, it's got acceleration, which is meters per second squared. Now, a lot of it goes back to what we did earlier with our units for kinematics. Meters per second, meters per second squared. It's the same idea here with radians per second, or radians per second squared, or just radians being a measurement of angle. All right, we're going to finish off this section with this last idea here. And the last idea is that we're going to utilize these equations here. So let's go back and look at our equations from earlier in the year first. We have our kinematic equations on the left-hand side. These are the big three kinematic equations that we started the year with. And we're going to take them and just translate them into rotational. Notice they're absolutely identical, but wherever there's a V, there's now an omega. Wherever there was an X over here, there's now a theta. Time is time no matter what, so T is still going to be T on both equations. Wherever, by the way, these are different. Take a look. Wherever there's A for acceleration, there's now alpha. That is different. It looks very similar. They look very similar. That's alpha. See the difference at the top of it? So this alpha is in place of this A that was here. This theta is in place of this X that's over here. Because linearly and rotationally, they are analogous to one another. So if we want to jot that down, V in linear becomes omega. X in linear becomes theta. A in linear becomes alpha. So these variables simply change their name or their character, but they're really the same. God bless you. They're really the same thing. Still acceleration, linear, rotational. Displacement, linear, angular. Velocity, linear, angular velocity. So the three variables on the right here for omega, theta, and alpha are simply our rotational equations that are using them. So the circled equations there are going to be three new equations on your formula sheet. You don't have to memorize them. They're on your formula sheet, but you have to know how to use them. So when you see radians, you need to be thinking, that's theta. When you see radians per second, that's omega. One of these. When you see radians per second squared, that's alpha. Your units tell you everything. Your units tell you everything.
Radians, what is what?
Radian radian per second squared. These are all listed already. Everything I'm writing here is in your notes. I put it right next to the formula every time on purpose. So next to the formula for omega, you're going to see radians per second. Next to the formula for alpha, you'll see radians per second squared. Theta, though, we measure in radians. We've discussed that. We went over radians as a new unit. But your units tell you everything for problems. Let's look at this next problem and use our units to help us. Take 20, 30 seconds on your own just to jot down what you think the variables are in this problem. Again, only based on the units. Use the units to help you. What is 100? And by the way, change 2100 to 2200. I didn't make that edit in your notes. Just change that to 2200, please. So what is 100? Radians per second. What is 2200? Radians per second. What is 30 seconds? And use the units to tell you what those values are. And then look at part A. Part A says, what is the angular acceleration? What is it? And that's alpha that we're looking for. So that's our question mark. We're told that the centrifuge rotor is accelerated uniformly. If it's accelerated, it's either speeding up or slowing down. It says from 100 radians per second up to 2200 radians per second. What do the units of radians per second represent? Which of our Greek symbols was radians per second? Yeah, omega, very good. And if it starts at 100, let's call that omega initial. If it ends at 2200, let's call that omega final. So it's starting at 100 and ending at 2200. And our time period is 30 seconds. So in part A, we're going to have to calculate alpha. And we know the equation for it already, and there it is. So we could all probably do that already for the first part. Part B is going to be the part that's a little trickier. Steve, is Mr. Blesser know that you're here?
Yeah.
You mentioned him?
I just texted someone.
How are we doing time-wise? This takes forever, I'm really sorry. All right,
How
fine,
many
yeah.
revolution has the six?
So you still have two short ones and then a long one?
Well, how much, what units is it? What? How do you know? Yeah. But how do you know?
2000.
Because that's just like the first section of what's gonna be. But you know how in
So I think that we're not going to use these big ones at all. We're just going to use the smaller ones.
I don't know.
meters per second squared.
Yeah.
These ones we're going to use. Where's the box? I got
What is it?
Radian per second squared.
What do you get for alpha? What do you get for alpha? 70, yeah. Good. And units for alpha? Good. Just like meters per second squared, it's radians now per second squared.
Wait, so the second part.
I don't, but I'm going to give you a break in 2 seconds. Can you wait? Yeah.
Revolution is question mark. This is what I drew on the test. Like revolution is question mark. That's easy.
Now, what's another, here, to help us with part B, let's think about this. Ready? What's another unit for revolutions?
Angle.
Revolution.
They measure angles, so what's the other unit?
Degrees.
Degrees. But what's the unit that we've learned now for degrees? Radians. So, when it says, listen, when it says, how many revolutions has it made, it's really saying, how much is the degrees or radian measure of the rotation that's happened? So what are we looking for, really? Theta. Theta is a measurement of how many degrees we've swept out. We've swept out as we rotate. That's what theta is. So we have two formulas we could use. for theta. We've got this one, and I'm just writing down what's on the previous slide. And then we have this one. We could use them both. Either would work, but which is better? They both would work, but which of them is better? What? Theta is already isolated here, whereas if we use the second one, we have to then solve for theta. But we could use the second one. Does everybody see what I'm getting at? It's your choice here, because we have enough variables to use either one. But I would not choose the second one. I would choose the first one. We're going to plug in all the values that we know. Everything is given. Omega I is 100. T is 30. Plus 1/2, 70 times 30 squared. And remember, my unit will always be radians for my answer for theta. Theta is measured in radians always. What do I end up getting in radians, Paula? 31,500? 34? 34? I must have made a typo on mine, my bad. For sure, right?
Yeah.
Okay, let me jot that down. I wrote 31,000. You could do that, but that doesn't... So that's how many radians we've elapsed, right? But we want to know how many rotations, not degrees. So to go to degrees next doesn't make sense, because then we'd have to go to rotations after that, right? So let's convert this. It is, but then we have to go from degrees. Remember, this is not degrees. It's radians. Yeah, that would be an extra step. What's our conversion? What's our conversion from like the first or second slide of all the notes? You can swipe all the way up. What's our conversion from radians to rotations or revolutions?
One rotation over 2.
Good. One rotation is 2 pi radians. And that's written down if you don't know it. One rotation, meaning a full circle, is always 2 pi. So take 34,500 and divide it by 2 pi. Make sure to put 2 pi in parentheses. Because you're really... isn't this really over 1?
Yeah, but what do you just...
34,500 times 1. See what I'm doing? Okay, that's right. Cancel your radians. How many rotations is 34,500 radians? 5,000 what?
50. Nope, yours is wrong. Look.
I had something else written down because I had a different answer for radians. I must have made a mistake when I typed it in quickly.
Okay.
Oh, I know the mistake I made.
I had like 50.
I know the mistake I made.
He got 54,000.
Yeah, also.
In math, I can't get over it. What's the probability?
So, is this right, Helen? Yeah? You checked?
5,000.
I got 5,493. So that's about.
And that's how many rotations it'll make. So think about this logically for a second. A centrifuge takes blood, it spins the blood to separate it into densities. It's making that many rotations in 30 seconds. It's spinning very fast. Extremely, extremely fast. Now there is one more problem. It is example number 8. I'm not going to have time to go through it right now. I want to give you guys a quick 3-minute break, maybe 3 to 5 minutes, then come back and we're going to start the data collection for this lab. Okay? Example 8 might not be in the notes that you have right now, but if you go to Moodle, you'll see I put new notes. I edited the notes once, and I added an example there. So if you want to even take a picture of it and put it on your screen,